Hello and welcome to class number 13. We've just finished taking our first test. Hopefully you started working on project 4. It's already been assigned. It is collected on class 15. So look for a date right there to the left of class number 15. That's when project 4 is due. Today we covered two different kinds of functions, power and polynomial functions. So let's begin here with our notes. Number 1. Lots of fill-in-the-blank questions today as we blitz through many functions you've seen in past math classes. We start with a 2-minute review of quadratics. Suppose f of x equals a times quantity x minus h squared plus k. Then blank are the coordinates of the blank of the blank. All right, you're going to pause the video in a moment and try to fill them in, but let me give you some hints because there are a lot of blanks here. This blank right here is the name of the curve that you would get if you graph that function. This blank is the name of a special point on that curve, which is either the high point or the low point. And then right here are coordinates. It's actually going to be some of the letters that you see in this function. So pause the video, see if you can fill in any of those 3 blanks, and then come back when you're done. So I've got h comma k as the coordinates of the vertex of the parabola. If a is greater than 0, the graph looks like this. It's quite happy. If a is less than 0, then the graph looks like this. It's sad. If it helps you remember, saying a greater than 0 means a is positive. A positive person is often smiling. A less than 0 makes a negative. A negative person can sometimes be frowning. Now suppose that f of x equals ax squared plus bx plus c. Then the x-coordinate of the vertex, remember that's the high point or the low point. Those two guys are they are each a vertex. The plural is vertices. The x-coordinate of the vertex is given by the formula. All right, you may or may not know this one, but pause the video, see if you can write down the formula. I'll give you another hint here. This formula is not just a fraction, but it's actually an equation. So pause the video and come back when you're ready. So I'll write down here the fraction that a lot of people say, okay, there's the vertex, but that's actually just the x-coordinate of the vertex. So I think it's important to highlight it's x equals that fraction. We can turn the standard form, that's this guy, or maybe we'll connect these two here. So standard form is that one, into the vertex form, so named because you can just read the vertex right off of it, with the technique called completing the square, which we'll see late in the semester. Number 2, 60 seconds or so on proportionality. X and y are said to be directly proportional if y equals k times x for some constant k. K is called the constant of proportionality. If 2 variables are directly proportional, then the graph of the relationship between them is a blank passing through the blank. Pause the video, see if you can identify the answers to those 2 blanks. Okay, so hopefully we see that the graph of y equals k times x is always a line, and it always passes through the origin, no matter what k is. Moving on, x and y are said to be inversely proportional if y equals k divided by x for some constant k. K is still called the constant of proportionality. In this case, the graph is a blank. Okay, this word is probably not as familiar to many of you. It's okay if you don't know this word. But the graph in this case is called a hyperbola, related to the parabola that we talked about up above. We'll see parabolas and hyperbolas in more detail late in the semester. Number 3, come up with an answer to this true-false question. All linear functions are examples of direct proportionality. If true, explain. If false, provide a counterexample. Pause the video here and come back when you're ready. Okay, so one way to think about answering this question is to just pick values of k and plug them into this y equals kx equation. So for example, y equals 3x, and y equals negative 7x. Those are examples of direct proportionality. And let's see, they're linear functions, and they work. They go through the origin and they're lines, and that's great. So those ones, yes, are examples of direct proportionality. But what about y equals 3x minus 1, or y equals negative 7x plus 2? Those are linear functions. So we'll circle in black here. Those are two linear functions, but they are not examples of direct proportionality. Direct proportionality means it's got to be y equals k times x and nothing else. Adding a 2 means it is not an example of direct proportionality. So here are two counter examples, which means the statement is false. Number 4, as an introduction to our review of power functions, try all parts of this problem. Some values of a function f are given in the table below. Values are rounded to 3 decimal places. So what you're going to do is work through parts A, B, C, and D. It's going to take you some time to go through these. This is a lot more time intense than the fill in the blank stuff we did up above. So pause the video, take your time, and work through all 4 parts of this problem. And you can come back when you're done. I'll also say that there is an answer key on the back of this page, but don't look at it until you've really given your best effort on these 4 parts. Okay, so let's work through these quickly together. Could f be a linear function? How do you know? Well, notice that the x's here are each changing by 1, so that's a constant change in x. And if it's going to be a linear function, then we better also have a constant change in y. So for example, this is a change of 3, but this is a change of 5.485, so automatically I know it's not a linear function because these things here are not all the same. So we'll say it's a non-constant slope, I guess is the best way to think of it. Part B, could f be an exponential function? How do you know? All right, so there's one thing in here that says automatically it's a no, because this function in the table passes through the origin. That's the first column. But exponential functions cannot possibly pass through the origin. In fact, they can't hit the x-axis at all. So that's cute and quick and all that, but probably more fundamental for why this cannot possibly be an exponential function is that if it were an exponential function, then instead of having these constant differences that we were looking for on the linear, we'd be looking for constant ratios. So for example, if you take 8.4 and change and you divide it by 3 instead of subtracting the 3, okay, so we get something like, 2.8. I don't know. You can type it in. And if it's going to be an exponential function, then it means every time you take a step to the right, like these blue arcs are, you'd be multiplying the previous number by the same thing, that same 2.8 every time. But if you take a look at these two guys and you take 15.5 and you divide it by the 8.4, you definitely don't get the 2.8 we get before. I mean, this number here is, maybe 1.9 or something. Type that in and just convince yourself that it's a different ratio as you step to the right. But exponential functions need to have the same ratio every time. Ratios aren't constant. Part C, do you think f could be a polynomial function? If it were, what would its degree have to be? Hint, look at differences. So our first project of the semester was about finding the differences, making difference tables. And we saw that if you had a polynomial, eventually you had a row that was all the same, and then the next row was all zeros. So if you essentially make a difference table here, I'm not going to do it, but if you make your difference table and do all the, subtract these, subtract these, subtract these, and then subtract these two numbers that you get and subtract these two numbers that you get and keep working your way down, if you eventually get a row that's the same, then sure, it's polynomial. But in this case, we run out of numbers before we get to a row that's the same. So I guess it could be a polynomial. In order to see that, we'd need more information, and then maybe the table could get longer, and eventually we'd find you know, a bunch of numbers that were the same. But given that we haven't, it is possible that this one is a polynomial, but the degree would have to be at least 5, because even after 5 differences, we didn't get to the same number. So the degree needs to be bigger than or equal to 5 if it's going to be a polynomial at all. Part D, this data can be modeled by a power function. This is one of our new ideas for today. A function of the form k times x to the p. X is the variable, k and p are constants. What would the values of k and p need to be? Hint, think about f of 1 to find k, and then look at another value and use a logarithm to find p. Okay, so let's give this a shot. So again, we're assuming that we start with this new kind of function, this new class of function. It's called the power function, k times x to the p. And first, I just want to point out this is different from the exponential functions that we saw before. Exponential functions are of the form a times b to the x. I don't know if those are exactly the letters we were using, but that's okay. So the idea behind an exponential function is that the variable is in the exponent. And it's kind of confusing to call this a power function because power and exponent are often used interchangeably. But a power function is a variable being raised to a power, whereas an exponential function has the variable in the exponent. Okay, so let's use some data points in this table here. So we know that, for example, f of 1 is 3. That's given from the chart, and we also know that let's pick the next number. F of 2 is 8 and change. And we're going to use these two facts to try to figure out what the values of k and p are. So on the one hand, we said that f of 1 is 3, but on the other hand, we have up here in black what the general formula for f is. So we can replace those x's with 1s and get k times 1 to the p. And we can do the same thing down here, plug in x equals 2 into that black function and get k times 2 to the p. And that first equation actually has something very nice happen. So let's write that. Ignoring this part in the middle here, I'm just going to cross it off because I'm ignoring it. I get 3 equals k times 1 to the p. But 1 to the p, 1 to anything is 1. So super, k is 3. Which we can then take and put into this function. So it was 8.485 equals, so k we just discovered is 3 times 2 to the p, which we have to find. And now we have an equation that we're going to solve for p. So let's go ahead and divide both sides by 3. And we'll type that into the calculator at some point. I'm just going to hold off for now. And how do we solve an equation where the exponent is where the variable is? We use logs. So let's hit both sides with a log. And then use that lovely property of logs that says log of something to a power. You can bring that power right down in the front. So the p comes down, multiplies by log of 2, divide both sides by log of 2, and we have our answer. Okay, so now we'll type that into the calculator to get our approximation for p, although I think in this case p turns out to be a pretty nice number. 8.485 divided by 3, and that whole thing is divided by log 2. So let's see what we get for the value of p, 1.49995, which is pretty darn close to 1.5, and I think it actually is 1.5. But the numbers in the table, most of them are rounded. So this 8.485 is rounded. If I'd given you more digits, then this would have gotten closer and closer to 1.5. So then write your final answer, which actually I'll write here in black, is the formula for the function. So it's in black towards the top of the screen, k times x to the p. We found k was 3 times x to the, and p is around 1.5. So that's our final answer here. So I think this is a good time to just do a quick detour over to Geogebra. So if you Google Geogebra, I'll write the words so that we can see it spelled out. And then go through the process to download some free software. Then you can follow along on your computer. If you just want to watch now and download the free software later, that's okay too. So, so pause the video if you feel like downloading it right now. Otherwise, you can check it out later. So here's GeoGebra. I'm going to make things a little bit bigger just so that we can see them better. So I'll go to font size. I don't have necessarily the latest version of GeoGebra, so the menu options might be slightly rearranged, but you should be able to find things even if my menu options are in different places than yours. Okay, so that's that. If I right click, one of the options here for me is grid, so that allows me to see the grid in the background. That's great. So what I'm going to do is plot 2 points. The 2 points that we picked were, what did we pick here? We picked the point 1, 3 and 2, 8.485. So let's plot those 2 points. And to plot a point, you just go to this input bar down here, you type parentheses, 1, 3. And it already typed the other parentheses because it's smart. Hit enter and great. There's the point 1, 3. And then the other point we said was going to be 2 and 8.485. So parentheses 2, 8.485. Hit enter. Super. Where is it? Well, it's off the screen. 8.485 is up above. Notice that it's written down a rounded version. It hasn't rounded. It hasn't forgotten, but right now the default is set so that we only have 2 digits. So if we go to options, that's where I'll find rounding, so I can have lots of digits in here. So there's the full number that I typed. So if you want to move the axes around, you click on this thing right here. Click on this plus sign, not on the arrow, but on the axes looking thing, and just anywhere you see blank space, not on the axes, see how the icon changes. Anywhere you see blank space, it's a hand. You click and you drag and you move it around, and lo and behold, we found our point right there. And I'm going to plot one more point. We didn't use it, but I'm going to plot one more point from this table, 4, 24. 4, 24, enter. Now here it's going to be tough because 24 is way, way up there. So yes, I can eventually find it if I keep dragging, but I'd really like to be able to see all these points at once. So we need to rescale. It's really easy to rescale. Again, I need that tool selected. It still is. Here I do want to go to the axis. It changes the icon. Click and drag down, and it changes the scale. And eventually we get to see all 3 of these points on the same set of axes. Okay, so what we're after is a graph that hits all of those points right there, and it's supposed to be of the form k times x to the p. Now we already know the answer, and if I just type in 3 times x to the 1.5, it will magically hit all 3 of those points. But I don't want to do that. I want to play around with GeoGebra a little bit more. I'm going to click on this thing right here called slider. And now that that's selected, I'm just going to click any place in the blank space, and it pops up some options here. Don't worry about that. Just click apply. And I'm going to pick a second slider as well, and we'll click apply. And I said don't worry about it, but actually I don't like the letters A and B. I would rather have them be K and P. So I'm going to do hit this undo button twice to get rid of those things. Okay, so let's see if that point is still up there. There it is. Okay, so I'm going back to slider, I'm clicking here, but I don't want it to be called A. I want it to be called K. So that's good there. And then again, that's still selected. So I'll just click anywhere in the blank space and I'll just type the letter P. Okay, great. And now what I want to do is graph the function that is our generic power function, k times x to the p. So we come over here and you type it just as it says, f of x equals k. Now you do have to hit the times key. Multiplication is implied if it were something like 2x, it knows it means 2 times x. But if you do kx, it doesn't know. If you're typing two variables right next to each other, two letters right next to each other, it doesn't understand multiplication is implied. So k times x to the, that's above the 6 key on my keyboard, p. And so right now it's going to graph 1 times x to the 1, which is just y equals x, which is going to be a diagonal line going through the origin. So there it is. And then I'm just going to start shifting things around. So if I increase k, okay, that changes the slope. That makes sense. But if I change p, then we get these new kinds of functions, and stuff, kind of funny stuff is happening. So there's when p is 3, you get this tail down here. But then as soon as I shift a little bit to the left, the tail disappears, and it pops up over here now when k is 2. And then it does all kinds of crazy things. So you can play around with this a bunch. But ultimately, I'm just trying to make something that hits all these points. So how about we try to make something that's, that's close to the points. That looks okay there. And then I'm going to change k, and that's actually like a vertical shift. It's kind of hard to see that it's a vertical shift, but it's shifting this guy vertically. And we just want to try to get close to all those points. So right now I'm kind of in between. I guess what I'd really like is for this line to be either all above the points or all below the points. So how about we change this thing right here? Maybe something like that. So it's all below, but it's kind of below by like the same, like not the same amount, but if I increase all these guys, you can see that we can get very close to all these points. Here, k is 2.6 and p is 1.6, which gives me a graph that's quite close to these 3 points. Now down here, I'll type in the actual formula that we found, which was, what did we say? It was 2.6. Is that what k was? I've forgotten. No, k was 3. So let's type in 3 times x to the 1.5. 3 times, and here I don't think I need to do the times key. 3x to the 1.5. And it's hard to actually see which one is which, so I'm going to hit this little guy right here, which is going to hide the graph of the 2.6 one. And so that right there goes perfectly through all the points, which is better than this one was, which was our estimate. We got pretty close to the right numbers. Okay, so that was just a little quick intro to some GeoGebra stuff. I encourage you to play around. If you've got ideas you want to explore in our class, GeoGebra might be a great place to explore. The software is completely free. Okay, moving on to the next page. The answers are above. We jump down to number 5. A power function is any function where the output is directly proportional to a power of the input. F of x equals k times x to the p. Now this formula we've already seen on the previous page. I'd encourage you to pause the video and make sure you understand this phrase right here. It's got that directly proportional business going on inside it. See if you agree that translating that phrase gives you exactly a formula like this. Which of these functions are power functions? How would we write them in the form k times x to the p? Okay, you've got 5 examples to go through here. Pause the video, identify which ones are power functions and which ones are imposters. And for the ones that are power functions, write them very explicitly in the form k times x to the p. Pause the video and come back when you're ready. Okay, part A, f of x equals 3 times x to the 2. Does it look like k times x to the p? Yes, it does. And in this case, k is simply 3 and p is 2, and we're done. Part B, square root of x over 10. Okay, it doesn't look like kx to the p yet, but we can make it look like kx to the p. So first I need a number in the front, not a number below. So if I want that 10 to move to the front, then I got to write it as a 1/10. So this is really 1/10 square root of x. And then the square root of x, it doesn't look like x to a power, but it could. So what power is the square root? Well, we know that's half. And now, yeah, lo and behold, it looks like a number times x to a number. A number times x to a number. And so in this case, we have k is a 1/10 and p is half. So this is another yes. Sometimes you have to do work in order to make something look like our regular form for power function. Part C. F of x equals 2 times 3 to the x. Does it look like a number times x to a number? A number, yes, times x, no, to a number, no. This is not a power function. Bonus points, call it an exponential function. That's what it is. It's very different. The form kind of looks similar, but where the x is completely dictates what we call the thing. And the reason we have different names for these functions is so that we can talk about them as families of functions. Part D, f of x equals 11. Okay, does it look like a number times x to a number? Well, let's see. This is 11 times x to, is there any power I can put up there so that the x isn't really here? Yeah, I can put x to the 0. 11 times x to the 0, now it looks like a number times x to a number. So surprisingly, it's a yes. K is 11, p is 0. Okay, and then part E, 17 over x to the 8. Okay, I don't like having 17 on top. I'm going to write that in the front, and I'll just put a 1 on top. But I can't have x in the bottom. So is there any way to rewrite it so the x is not in the bottom? The answer is yes. We know that x to the 8 in the bottom is the same as x to the minus 8 on top. So lo and behold, yet another power function. The k in this case is 17, and the p is negative 8. So again, the point is that power functions can come in many different forms, but ultimately they have to be able to be rewritten in a specific form. And that's this form up here. Number 6, how could we go about finding an equation for a power function based on some data? Let's find a power function that passes through the points 2, 3, and 6, 5. Okay, so we begin with our standard starting formula for power functions. K times x to the p. And we're going to plug in our data points. We know that, for example, f of 2 is 3, and that f of 6 is 5. But we also know that we can plug f of 2, we can plug 2 into the function that's up there in black. Plugging 2 in for the x gives me k times 2 to the p. And down here, plug 6 for the x in the same black equation, k times 6 to the p. Okay, and then I'm going to put a little line through these two and then just rewrite the equations over here. 3 is equal to k times 2 to the p, and 5 is equal to k times 6 to the p. So that's our starting point. Okay, there is a cutesy and slightly more efficient way to solve for k and p than we're about to do, and that involves dividing these two equations by each other. Because if you do that, the k disappears right away, which is great. But it's just kind of a trick, and it's generally not a very useful trick, even though it would save a little bit of time on this problem. So I'm going to do what I consider to be not a trick, but a more broadly usable technique, and that is the technique of substitution. So we're going to solve one equation for one letter. I will choose to solve this equation for k. You could just as well choose to solve the other equation for k. I'd be reluctant to solve either equation for p because p is buried in an exponent, which makes it less accessible to us at the moment. So we'll solve for k, and we get 3 divided by 2 to the p is equal to k. And then we're going to take this value of k, and we're going to shove it into the other equation where the k is. So that becomes 5 equals, I'll leave a space there, k times 6 to the p, but instead of k, we've discovered that k is really 3 over 2 to the p. Okay, the benefit here is that this equation has only p in it and not both p and k. We still have some work to do in order to solve this equation, however. So let's rewrite here. 5 equals 3 times. Now what I want to do is mush things with the p's in each other, mush the things with the p's together. So I'm just going to make the fraction have both terms with p in it. And then we're going to use this really nice property of exponents, which probably doesn't get used very often, but I'll write it here and remind you, if you have a to the, let's write it this way, a over b to a power, that's the same as a to the power divided by b to the power. Hopefully that seems familiar. And so we can use that to rewrite this term right here. because it looks like this thing on the right. It's a to a power divided by b to that same power. So apparently, according to that rule in red, we can mush those two things together and put them in parentheses and just use the power once. And what goes in the parentheses here is 6 over 2. Okay, great. We'll rewrite that. That's really 5 equals 3 times 3 to the p. I'm trying to get that exponential part by itself, so divide by the first 3, and we get 5/3 is equal to 3 to the p. And now the variable is in the exponent, so we'll hit both sides with a log. Okay, and I'm going to be really lazy here and combine this step and the next one and take advantage of the fact that log of something to a power, you can take that power and move it to the front. So I'm just going to put that right here. Last step to solve for p means divide both sides by log 3. So we get log of 5/3 divided by log of 3. So that's the value of p. We'll type it into the calculator in a moment to get a decimal approximation. But let's just finish this real quick to get the value of k. So let's find the place where it says k equals, up there in green, circled here towards the top. So this is the best place to go to find k. So we're going to take that thing and put it down here. Say, okay, we know that k is definitely 3 divided by 2 to the p. But p we just found here on the bottom left is this long complicated thing, log of 5/3 divided by log of 3. So that's the value of k. So let's go ahead and write these two things as decimals. So we'll very carefully type in the value of p first. So we need log of 5/3, and that's divided by log of 3. So that's p, about 0.47 or 647. And then k is 3 divided by 2 to the, now, oops, 2 to the. Now, I don't really want to type in that whole thing again, so instead of typing it in, I'll just do second answer. That's a lot more reliable, I think, than trying to retype that whole complicated expression from up here, but now you're trying to type it as an entire power down there. So 2.17 and change. All right, so P was around 0.465, and K we saw was 2.173. So then our final answer here, remember it started off way back as K times X to the P. 2.173 times X to the P, 0.465. Okay, so we've got that. We've got our formula. Maybe real quick, and in fact, we'll just highlight it here. But maybe real quick, we'll just go to Geogebra and see if Geogebra confirms that that graph right there hits the 2 points that we started with. Okay, so we begin here. I'll right-click and turn on the grid. I'll change the labels to make them, oops, change the font size to make it bigger. And then I'll plot our 2 points. So the 2 points we were given in the problem were 2, 3, and 6, 5. So parentheses 2, 3, enter, parentheses 6, 5, enter. And then the last thing is the function that we just found, f of x equals. So we'll just copy it from here, 2.173 times x to the 0.465. So if I've done that right and I hit enter, we should get a formula or a graph that hits both of those points. There it is. Next page, number 7. One nice thing about power functions is that there aren't that many different kinds of graphs that a power function can have. As an example, you are very familiar with the graph of f of x equals k times x squared. graphs of f of x equals k times x to the fourth, and f of x equals k times x to the sixth, and f of x equals k times x to the eighth, notice they're all even positive numbers, are all basically the same as the graph of f of x equals k times x squared. Here are quick sketches of some of the different kinds of power functions. In each case, we are graphing f of x equals k times x to the p, and we'll assume that k is bigger than 0. So if p is a positive odd integer, so just again, every time we're going to be graphing this thing highlighted here in yellow. So a positive odd integer. So that means I'm thinking about k times x to the 1, k times x to the 3, k times x to the 5. So actually k times x to the 1 is kind of an outlier. So let's hold off on that one. Kx cubed, kx to the 5th, kx to the 7th. If k is positive, then all of them look like this kind of thing. Functions that hit the origin, increasing the whole time, concave down to the left of the origin and concave up to the right. And now we'll put here in a different color, k times x to the 1, which is a special case. It's a line, goes through the origin. Yes, it's increasing the whole time, but it doesn't really share much else in common with the curvy things that are graphed in purple. Okay, next one, p is a positive even integer. So here we're thinking kx squared, kx to the 4, kx to the 6th. And they all kind of look like our friend the parabola, decreasing until the origin and then increasing. P is a negative odd integer. So now I'm thinking about k times x to the negative 1, or x to the negative 3, or x to the negative 5. And I'll just say that that if you've ever seen the graph of y equals 1 over x, then you are looking at the graph of k times x to the negative 1, but just maybe a different value of k. And so y equals 1 over x looks like this. It's got two different branches, one of them in the first quadrant, the other in the third quadrant. Never hits either axis. Two axes are asymptotes. And that graph is actually called the hyperbola. I mentioned that on the first page of today's notes. Next one is another one that you may not be as familiar with, but p a negative even integer. So now it's like k times x to the negative 2, negative 4, negative 6, etc. Actually looks quite a bit like the graph we just drew on the left. In fact, the first part is almost exactly the same in the first quadrant there. But when you square a number or fourth it or sixth it, it can never be negative. So that part that's in the third quadrant can't have negative y values on it. So it has to become something with positive y values on it. And it just flips up into the second quadrant. Okay, and then the last two here at the bottom. P is 1 divided by a positive odd integer. Okay, so now we're thinking of something like k times x to the 1 divided by a positive odd integer. 1 divided by 3, 1 divided by 5, 1 divided by 7. Notice that I've skipped 1 divided by 1. Again, that's a special case, so I'm not going to include it there. But before I graph that, let's graph this last one. P is 1 divided by a positive even. So now we're looking at x to the 1 over 2, x to the 1 over 4, x to the 1 over 6. But you know x to the 1 over 2 is really square root of x, and I'm hoping you know what the square root of x looks like. Hits the origin, increases quickly in the beginning, and then slowly. I need to make sure I draw it so it doesn't appear to level off. It's growing more and more slowly, but it grows forever. So all of those 1 over even positive integers look like that. And I wanted to draw that first because coming over here to the 1 divided by the odd positives actually looks pretty much exactly the same there. But this one continues, actually. It hits the origin, but then it continues. So let's make sure we understand why this graph here doesn't continue. Like, it seems like it has two choices. It could turn around, or maybe it continues that way. But the problem is here, okay, if it did this, then it wouldn't be a function. All right, so it's not that. But if it did this over here, it would mean, for example, that you could take the square root of -2 and get some number. And we know that the square root of -2 is imaginary. So we don't draw it here because we're only drawing graphs of real functions. But over here, when I look at the cube root of -2, which is on the graph of this first function, well, the cube root of -2 is a perfectly good real number which you can plot. And so this one continues, and it's symmetric over the origin. So using GeoGebra would be a really, really great idea to experiment with these kinds of things. I've just kind of said, hey guys, here's what these look like, but there's no reason for you to believe me, so go play around on GeoGebra and go into GeoGebra. I'll even get you started here. But if you are starting with a blank GeoGebra page, get yourself two sliders, one called K, and if negative 5 to 5 isn't good enough for you, you can go negative 10. Actually, the K is not really the issue. It's really the P that's the one you'll want some freedom on. So you can make P go from like negative 10 to 10. And currently it's going by increments of 0.1. So maybe we can just change that to increments of 1, and that's okay. And let's make the slider, hit the slider tab there, make it a little bit bigger. This just tells you the width of the slider is 100 pixels. Let's make it 400. So you can see that's 4 times as long as the previous one. And then you just come down here and your graph function f of x equals k times x to the p. Don't forget to use the times symbol. Okay, great. So it looks like that, and then as you move p to the right, so there's x squared, x cubed, x4, x6, x5, x6, x7. Great, all that is fine. Now, I'm going to let you experiment what happens when you make p negative, because we did talk about that in our graph here. So drag this thing to the left, and you'll see some things that look like the hyperbolas that we drew, or the hyperbola we drew. And so that's fine, so that takes care of those. But what about the ones where it's 1 divided by an even, a positive even number? So you could come in here and you could say, okay, I don't want to graph just this function, but I'd actually like to graph k times x to the 1 divided by p. And then you can play the game about what does it look like when it's 1 divided by p. And so I'm not going to play around with this here. I will let you experiment, but I think GeoGebra is a great tool for this kind of experimentation. Okay, last page. With practice, I'd like you to be able to quickly sketch the graphs of power functions like these. Now this is without a calculator. 8x to the 41, negative 3x to the 1/4, 10 times x to the negative 6. It says try them later. I mean, heck, if you want to, just pause the video, get a blank piece of paper, and try them now. Don't spend too much time on them. Essentially, I'm just asking you, these three functions all look like the functions that we drew on the previous page. You just have to figure out which three we're talking about. One little thing I'll say is that negative means it's going to not quite look exactly the same as one of the ones that we drew, but it will look very similar. So, so play around, and then you can check your work on your calculator, or maybe better yet, on GeoGebra. So feel free to pause the video and come back when you're done. But we'll just go through these last few vocabulary things when you're ready. Number 9, a polynomial is a sum of power functions where the powers are all non-negative integers. So there's lots of notation in this function right here, but I'm just going to write down some examples. F of x equals negative 3x to the 7 plus 2x to the 5 minus 4x plus 6. So that right there is a polynomial function. And I just want to highlight that polynomial functions have very restricted rules for what those powers are allowed to be. It's got to be positive, it's got to be non-negative integers. So it's okay to have a power of 7 or 5 or the invisible 1. It's even okay to have a number at the end because that's like x to the 0, 6 times x to the 0. What is not okay is to have something like square root of x, because that's x to the half, and a half is not an integer. So square root of x is no good. Also no good is 1 divided by x cubed, because that's x to the negative 3, and we're not allowed to have negative powers. Okay, a couple more fill in the blanks and then we're done. The a's are called the coefficients. So the numbers in front of the x's. A sub n is this guy right here. It's the first one, the one that goes with the highest power. It's got a special name. It's not just any old coefficient, but it's the leading coefficient. A sub n x to the n, that's not just the coefficient, but the entire term, is called the leading term. And it completely determines the end behavior of the polynomial. We will talk about this in detail next class. The blank is n, the highest exponent. So we've used this word already, but the highest exponent for a polynomial is called the degree. Values of x for which f of x equals 0 are called blanks of the polynomial. So those are called kind of uncreatively zeros of the polynomial. And they're exactly blank of them. Okay, let's see. So if I gave you this equation up here in red, I said, figure out what values of x make this thing equal to 0. Well, that's really hard to do, but we can know without any work how many answers we'd expect. How many values of x make that equation equal 0? And the answer is 7. It's always the highest power. That's a really famous theorem in mathematics. Highest power of the polynomial tells you exactly how many zeros there are. You might play around with linear equations, something like 3x minus 4 equals 8. In fact, why don't we make it equal 0? 3x minus 4 equals 0. You can solve for x. How many answers will you get? You will get exactly 1, which lo and behold is the power up there. And if I asked you to solve x squared minus x minus 12 equals 0, so you can try quadratic formula or factoring if you wish. And you will find that you have 2 different solutions there. They don't have to be different, but there will be 2 solutions. And so filling in the blank here, the values are called zeros, and they're exactly n of them, whatever that highest power is. Places where the graph changes from increasing to decreasing or vice versa are called, okay, so here we're talking about places where the graph changes from increasing to decreasing. So that would be a maximum point, a high point on the graph. You could also have minimums, low points, but altogether they are called extreme points or extrema. There's a plural for extreme points. And there are at most blank of them. So it turns out that the number of highs and lows is at most 1 less than the degree, n minus 1. Okay, again, hopefully you're working on project number 4. Homework and reading and questions of the day are in the usual place.